Welcome to another video where I talk about C++. Today's topic is an advanced one, but something that might get the more junior of the programmers into trouble. I have prepared this fairly simple motivating example here in Godbolt, so let's get into it. So what I'm trying to figure out here is the size of a few structures that I have. One is unordered map, and there's a unique pointer as well. So I have a print size of, which just gets a type. It's templatized on a type T. It gets it and it prints out a string like this. Size of my hash is 2. So I have I'm here printing size of a bunch of structures here. So let's see what's happening. I have an unordered map of pairs, a pair of float and int, mapped to another int. And I'm using the default hash here, this std hash here. So the size of this unordered map is 56. As you can see, it's printed here. And then I have another unordered map that has a structure that is from a structure of int and float to int. Here is that a structure, it is simply an int and a floating point. And I'm using my own hash I have written here because I'm using a structure that doesn't have a std hash for. So what I'm doing here for the hash is just instantiating a hash for int, std hash, and a std hash for floating point, and then I'm calculating the XOR of each hash. And then I when I get the size of this, when I print the size of this, it is 64. It is 8 bytes more than this 56 that we have here. The same thing kind of happens on unique pointer. I have a unique pointer of void, which holds a void pointer, and the size of it is 8. Then I have a unique pointer of void again, with a function pointer as a deleter. The size is 16. So the only thing that is changing here between this unique pointer and the other is the deleter. The only difference is that the deleter is here is a custom deleter, and that the deleter is a function pointer. And you would kind of imagine if you would have to hold a vector of these pointers, you will have to consume double the size that you would essentially need if you were to delete them by hand one by one. This is kind of something that happens when you're kind of dealing with C interfaces. You probably wouldn't use free or malloc somewhere in the naked form, but probably some other C libraries interfaces will look something like this. There will be some function that frees something, and there will be some function that allocates something, and you don't want to maintain the lifetime by yourself. You want to maintain the lifetime using a unique pointer, and you can do it with something like this. But as you can see, it is costing you double the size. And this is not just something that affects the size, but also affects the performance here. I have the same thing. I have a vector here. I'm reserving my vector, so I'm not growing my vector in my benchmark. And so since I'm not growing my vector, I'm not taking into account the allocation, the time spent on allocation for the vector. And then I'm emplacing a null pointer to my unique pointer here, which is a unique pointer of void, and a custom deleter. What the deleter does is nothing. It just prevents the optimization of pointer. That's it. I have two deleters, a structure and a simple deleter. I will talk about why structure is here and why is structure better and doesn't have any of the problems of the pointer here later in this video. And as you can see, the structure one is fairly more optimized, maybe 10%, 10%, yeah, something about 10%. And yeah, what I'm doing here is just passing a null pointer to the deleter, nothing else. In placing a null pointer to my unique pointer with custom deleter. Deleter does nothing. And then at the end, I'm just clearing my vector, which is simply just destructing every element. Same happens here, but with different deleter. My deleter here is a function pointer rather than a struct, as we have here. So I'm passing my deleter and null pointer to my to construct and in place a unique pointer here, and then after in placing 1024 unique pointers, I'm clearing everything up, and here's the deleter I'm using. And you can see some kind of a more stronger performance deficiency here when you're actually taking into account the time that you're spending to allocate more memory. Because here my vector is allocating twice the memory, and you can see that it is way more. I've edited this, so yeah. So this is taken just twice, almost double the time, more than double the time, just because you're using a bad deleter here, a function pointer as a deleter rather than a simple structure. So let's see why this is actually happening. So to show you that what I mean when I'm talking about using a simple structure here, we can do the same here. For instead of using a pointer, I'm going to use my deleter structure here. And you will see that after it compiles, let's see, okay, you will see that the size has now changed to 8 rather than 16 that was before. So using a structure has something to do with the size of the unique pointer here. So let's see what is happening here. So there's this concept in C++ that every object in C++ has to have a unique address, except when you're inheriting from the object. So what does it mean to have a unique address? So let's start here from my hash. We know that stud hash is usually implemented stateless, and hence, let me make it close to make sure that it is stateless. All right, so yeah, standard hash is usually implemented as a stateless structure. So this hash structure is actually empty, and the size of this int hash should be 0. But again, as I said, every single object in C++ has to have a unique pointer. So if you get the size of unique address, so if you get the size of this int hash, it is 1, actually 1, not 0. And that is to make sure that these two consecutive members of my hash don't fall into a single address, because that would cause int hash and float hash to have the same address. And yeah, and as you can see here, when I'm getting the size of my hash here, it is giving me 1 byte for each. All right, so we said that there is an exception for this, and that exception is when you inherit from it. So if I were to inherit from my int hash, okay, not int hash, but rather stud hash of int, and inherit from my float hash here, and instead of using my members here, I would use simply this. Okay, let me see if it's going to complain that it is ambiguous. I don't think it is going to complain, but let's see. Compile for me, please. Okay, what is the error I'm getting? Const int to my float is here. Okay, let's be a bit Oops, I shouldn't have done that. I should have done this. All right. Okay, so it compiles. And let's see our sizes here now. Now the size of my hash is 1 because you can't have a size of 0 as we said. And now the size of my two unordered maps are both 56. Okay, so this is one solution to the problem. And there's another solution that is introduced in C++20. But before we go to that solution, let's take a look at this. If I declare my structure final, that means that no one else may inherit from this my hash structure here. So hence the implementation on this specific standard library that I'm using, which is probably a Linux standard library, GCC standard library for version 10.3. And you can see that this final keyword here just prevents the standard library to use that inheritance trick to avoid allocating extra space for this hash. And it allocates 8 more bytes for my unordered map here. So the solution for, let's just recap everything. The solution for not allocating extra space for empty structures is to inherit from them. That is previous to C++20. And I am compiling actually at C++20 here, so I'm going to test the solution that is provided in C++20. So the standard library implementations always take this into account, both unique pointer and unordered map on hash. Unordered map checks your hash. If the hash function is an empty function, empty hash structure is an empty structure, it will simply not allocate any space for it and just inherit from it. And same goes for unique pointer and deleter. The unique pointer will inherit from your deleter and won't allocate any extra space for it. So on C++20, there is a better solution for this, and that is the attribute no unique address. What this attribute says is that if I have a member here, let's revert the code back to when we had a member. So if I have a bunch of members here, I can rather declare them no unique address. That means I don't need a unique address for this member. And same goes for my next member. I don't need a unique address for this as well. So what happens is kind of the same result as we were inheriting from these. Let's take a look again. You see that my hash here has a size of 1, and my unordered map, both of my unordered maps have sizes of 56. All right, that's the end of this video. Thank you for watching, and sorry for the clickbaity title that is going to be on this video. See you guys.